science suffers. We have learned that science itself flourishes only when you have openness. When we publish our results in journals and everyone can read them, or put them on the internet and they're available to everyone anywhere immediately. I believe that this method that has been honed and improved over the last 400 years is in of itself is of great social value to humanity. And it has implications for how we live and how we interact with one another. For a healthy scientific culture truly requires an open society. Scientists among themselves are a very open society, and anything that stops discussion, stifles debate, promotes authority is bad for science. Science promotes tolerance. We might be wrong. Any idea I have might be wrong. So I must tolerate other people's ideas, even if they're different than mine. And that is a very important human value. And in effect, science promotes democracy. Because we all, as scientists, we all understand that everyone is equal in science. I can give a lecture describing my theory, and a bright young student with no credentials can get up and say, "But you're wrong." And he might be right. So these are values of the scientific approach, which we've adopted maybe only because they're good for science, but they're also good for tolerance, for democracy, for openness, transparency. But of course, the main goal of science is to provide knowledge of nature. We human beings are programmed biologically for our survival to construct models, explanations of the world. And with the scientific method, we've learned to do that very well. And I'll give just a very quick history of physics, astrophysics, cosmology, and biology. Physics, of course, is the oldest science, the queen of sciences, we physicists say. It's been going strong for 400 years and is an amazingly successful enterprise. 400 years is not a long time. That's the life of 6 people, one after another. So just 6 lifetimes ago, Galileo and Newton started the scientific approach to physics. And now we have a theory that seems to explain just about everything until we get down to the very, very short distances. Astrophysics, people have been doing forever. Astronomy, looking at the stars, trying to understand what the universe is made of. In the last 100 years, we have gone from thinking that we lived in a static Milky Way and that was the universe, to understanding the whole history of the universe from almost its beginning till now. In biology is perhaps the youngest of the sciences and has made enormous strides, but still it's in its infancy. So let's start with physics. And I've tried to summarize in a few sentences what we've learned over 400 years. At the beginning, Galileo and Newton discovered the basic laws of motion that govern motion of bodies and the symmetries of nature that we've learned more and more are the basis of that dictate the forces that act on bodies and make them move. We have unveiled the structure of matter, the underlying atomic structure of matter, whose atoms form the constituents of all the matter we see naturally around us. And we've learned that they are governed by strange laws of quantum mechanics. And in the last 100 years, we have constructed a comprehensive quantitative theory of both atomic and nuclear forces, identified the basic constituents of matter, and now we are engaged in an ambitious attempt to try to unify all these forces together. We're far from that goal, but we're working on it. And it really all started, as I said, only 6 lifetimes ago with Galileo, who, aside from being a great experimentalist and developing the telescope and other experimental tools, was also a theoretical physicist. And he understood the first time that the language of science is mathematics, which is why it's often so hard to explain physics to people who don't know mathematics. Mathematics, our most highly developed form of language, is necessary to understand nature. And the more we learn about nature at its most fundamental level, the more we discover a beautiful mathematical structure behind it. Newton used Galileo's insights and the mathematics he developed and his intuition to construct a universal theory for the first time that both explained apples and planets, subject to the same law of gravity, and a theory strong and powerful enough that he could predict and calculate with precision the motion of the planets. And Newton's theory was so powerful that it set the stage for all of modern science. This goal of constructing a quantitative explanation of all phenomena continually subjected to experimental test. And this was all done just in the first 100 years. In the 19th century, Maxwell unified the phenomena of magnetism and electricity and realized that light was a wave in the electromagnetic field that described electricity. And all of the phenomena of light and electricity and magnetism could be summarized in a set of beautiful equations that you can put on one t-shirt. This was also the century of the Industrial Revolution, where we learned to construct machines and transform heat into mechanical work. We understood heat and energy and entropy. And this is one of the heroes of that development, Ludwig Boltzmann, who understood what entropy was really about. And finally, in the 20th century, we completed the atomic theory of matter, starting with the realization that all ordinary matter is made of atoms. Atoms have a structure. They're not just little hard dots. They have a structure. They consist of a very small nucleus and an electron cloud whirling around that determines the structure of individual atoms and molecules. So atoms, we understood, are electrons revolving around nuclei, and in order to understand their structure, one had to invent quantum mechanics, a whole new way of looking at the world, replacing classical mechanics. Here are some of the heroes that did this great development in the beginning of the 20th century. Planck and Einstein, Schrödinger, Bohr, Heisenberg and Dirac, and of course Rutherford, who discovered the nucleus. And as it has turned out, over the century and continuing today, we understand that the collective behavior of atoms is responsible for all the properties and phases and behavior of matter, including all of chemistry. And supposedly all of biology is determined by just these atoms interacting with each other. The basic equations that describe this could also be written on one t-shirt. That's not to say we understand how biochemistry and biology work based on that t-shirt, but in principle, we think that is the case. Also in the 20th century, we learned that space-time is more complicated than we thought. It's dynamical, said Einstein, and mass and energy curve space, giving rise to gravity. And finally, in the last half of the 20th century, my generation, we completed the so-called standard model, or the standard theory of particles. We identified all of the elementary particles of nature that constitute ordinary matter, and they consist of quarks inside the nucleus, electrons, a cloud around the nucleus, accompanied by neutrinos, very light particles. We discovered 3 families of such particles, and most importantly, we identified the 3 basic forces of nature in addition to gravity. Force of electromagnetism was known for quite a while, but in the 20th century we understood the force that acts inside the nucleus, the strong and weak nuclear forces. And I'll say a word about the strong nuclear force because that's the one that we figured out. So, the nuclear force. This was a very hard force to understand, since it operated inside this teeny little nucleus that is buried inside the atom and hard to peer within. And as we began to look inside the nucleus, experiments showed, just as I was leaving graduate school, that the proton looked as if it were made out of freely moving point-like particles called quarks.